the screen. So hopefully you can see the full screen.
Yes.
Yeah.
And we also can see Professor Smoyanov. Nice.
Right. So again, I'd like to thank the organizers for inviting me here. The talk I'm going to give, it's actually a relatively old result that, as it stands, going back for me, 2016, 2017. However, it's something that's sort of come back again. It was relatively important at the time. It also fits somewhat into the remit of this workshop on semi-groups, and a technique we've seen a little bit of today, and we'll hear a little bit more of, namely Chernov's theorem. So the title is Dynamical Decoupling. So dynamical decoupling is a very important technique that's used in quantum control. The idea is you send very fast pulses to a quantum mechanical system, usually magnetic pulses, and this can usually stop any sort of Hamiltonian evolution that's occurring. There's a question of how effective this is in the presence of noise, and that has received quite a bit of attention. So I want to put this related work that's been going on in the context of quantum dissipative systems. So I'll start off with a prologue, and the prologue is really just a reminder of the Hudson Sarati theory. So we're really interested fundamentally in quantum open systems, quantum Markovian systems, and Hudson and Sarati were able to give a complete theory of Markov dilations of open quantum systems, and in particular, ones which, when you traced out over the reservoir, the environment, you were left with a quantum dynamical semi-group, so a one-parameter semi-group of completely positive maps, in particular with a generator which was of Lindblad type. So just to run through very quickly the setting of Hudson Sarati, they come up with an environment for quantum mechanical system which lives on a Bose-Fock space. In their dilations, the Markovian dilation, they introduce bosonic operators, a creation process and an annihilation process, A and A dagger, and they satisfy a continual form of the commutation relations. And they have a stochastic calculus, which is a generalization of the Ito calculus. So for instance, for a self-adjoint operator H, which will be the Hamiltonian of the system, and coupling operators L, they construct a unitary process on the total space, which is the Hilbert space of the system, tensored with the Bose-Fock space environment. So the equation in green gives you the effective equation of motion. So it's an equation for a unitary, that's the unitary dynamics. And at time zero, you'd initiate it as just the identity operator. So identity on the system tensor with identity on the Fock space. So if you look at the Heisenberg picture, if you like, you take a system operator X, so it's ampliated with the identity on the Fock space. You conjugate it with the unitary process, so that's U star on one side and U on the other. And then you basically average this over the vacuum state of the system, of the Bose-Fock space, you're then left with a family of maps on the system algebra, and these will be completely positive maps. They'll form a semigroup, and the generator will be of Lindblad type. So in the equation in yellow here, we've got a typical Lindblad generator. At the end, you'll see the Hamiltonian part. So that's the usual commutator of the observable X with the Hamiltonian operator. You also have a dissipative part, which involves the coupling operators L. So more generally, you can have several of these coupling operators, which just means you have several independent Bose operators put in. Okay. So the framework here is on the Fock space over L2 of R. So the real line here we can think of as time. In quantum optics, you might think of this as a laser beam. So it's photons traveling along the beam. At the origin, you've got the system. So you have the beam coming in down one axis and going out on the other side. What's quite interesting about this is that even though you have this unitary process, it's strongly continuous. It forms a semigroup. So it's a semigroup only, so you don't have a stone generator. However, if you look at the free shift along this line, the free shift, okay, that just propagates states down the time axis. You can actually show that the unitary is really a perturbation of this free shift. You're effectively in the interaction picture. So you can write this unitary quantum stochastic process as just subtracting off the free evolution. There's a unitary process V of t, but that forms a strongly continuous one parameter group. It'll have a stone generator. And the stone generator, it was a long-standing problem to solve for what this actually is. It came out in 2000 in a paper by Gregorati, but people like Alexander Chebatarov, Willem van Waldenfels, and others have worked on this. It's a rather singular operator, given here in blue. It involves these little b's. The little b's are supposed to be annihilation operators, so they act on the symmetrized wave functions on Fock space. So B0 would effectively evaluate one of the symmetrized coordinates to be 0. And we need B0 plus and B0 minus because we right and left hand limits. So at the very bottom here, I've got the boundary conditions, which basically says that the functions in the domain satisfy a boundary condition discontinuous at the origin. And effectively, that's an input-output relation. So it's the boson field coming in, hitting your system, then going out. It's singular, and that's the Markovian element of this. Okay, so that's the prologue. I'll tell you a little bit now about dynamical decoupling. So to give a very, very simple example just at the outset, suppose we've got a qubit system, and we consider the set of 4 unitaries just consisting of the identity and the Pauli matrices. So the observation is that if you take any operator X and conjugate it with each of these 4 unitaries in turn, and you then average over the 4, you basically get an operator which is proportional to the identity. And the proportionality is just 1/2 the trace of X. In other words, the average in the least informative state, the one with density matrix 1/2 the identity. So more generally, a dynamical decoupling set on, say, a finite dimensional Hilbert space, d-dimensional, is a set of unitaries, so that if you average over the conjugation of an observable x with these unitaries, you get something which is proportional to the identity. So in general, 1/d, the trace of x. Pardon, that should be an x there. So this averaging process using these unitaries sort of trivializes things, pushing you into just multiples of the identity. So here's the idea of dynamical decoupling and how in practice it's used by physicists. You have a particular quantum dynamics. So let's suppose it's an open system. It's described by this quantum dynamical semigroup with a Lindblad generator L. The idea is that you apply, say at random, elements from this dynamical decoupling set. Really, you apply them as instantaneous kicks. This could be by just having a magnetic field pulse along one of the axes in the qubit example, but more generally done as follows. And the idea is you do this very, very fast. So say on an interval 0 to t as time, you chop it up into small time segments. And at the start of the time segment, you multiply by, say, one of these unitaries from the dynamical decoupling set, say Vk, you multiply by Vk star, then you multiply by Vk at the end of the interval. So the idea is you do this infinitely quickly. The limit should give you, again, something which is a completely positive semigroup with an average generator L bar, which sort of looks like this. What's of interest to note is that if your system has a purely Hamiltonian dynamics, the dynamical decoupling in this fast limit will effectively freeze out the dynamics. So if you have some unknown Hamiltonian, you can get rid of it via dynamical decoupling. Okay, so that still leaves the question of what's the effect of residual noise. Now, in 2015, the following paper came out, and this came to a rather surprising conclusion. And the title is Distinguishing Decoherence from Alternative Quantum Theories by Dynamical Decoupling. And I'll just read you the abstract. A long-standing challenge in the foundation of quantum mechanics is the verification of alternative collapse theories, despite their mathematical similarity to decoherence. To this end, we suggest a method based on dynamical decoupling. And down further, as part of the analysis, we proved that unbounded Hamiltonians can be perfectly decoupled. Okay, so first of all, looking at the title, alternative quantum theories. What's an alternative quantum theory? Well, what they mean is any theory supposedly describing the quantum world which is not based on having a Hilbert space and a dynamics coming from a self-adjoint Hamiltonian. Okay, so here's their argument. You consider the most general situation of a system and reservoir. So your system is going to be a d-dimensional Hilbert space. You take your Hamiltonian to be a combination of preterms, so there's a system-only Hamiltonian, the free Hamiltonian of the reservoir, and then some sort of interaction which couples the system to the reservoir. Okay? So what they want to do is, in principle, allow these operators here to be unbounded. In the case where it's bounded, there's well-known results by Lorenzo, Viola, and also Mill, where they obtain error bounds, which effectively ensures that dynamical decoupling is still going to work reasonably well. Okay, so it's still a proper theory to use, and the application to real experiments show this. So the question is what to do if your Hamiltonian is unbounded. So we're first of all going to make an assumption here, and the assumption is that the domain of the Hamiltonian is dense. So with that assumption, the idea is fairly simple. You just use the Chernov's theorem. So you start off with the following operator family Ft. So it's just the evolution due to the Hamiltonian. And then you multiply by these decoupling operators on the right and the left. So you conjugate unit with these unitaries. So what you can check is that as the limit t goes to 0, so basically the derivative of f at 0 for psi in the domain, you're basically getting the effective average of your Hamiltonian with unitary conjugations by the elements of the decoupling set. So here, the free Hamiltonian should, of course, vanish, or effectively be replaced by a constant, but so too should the effect of the coupling operators to the system. So in a sense, you're left purely with the free dynamics of the Hamiltonian itself. So even if it's unbounded, the claim is that you now have decoupled your system completely from the environment. So the conclusions they have is the following, that infinitely fast dynamical decoupling works for unbounded Hamiltonians. It's going to freeze the dynamics of the system, but also potentially any interaction, so that all you're left with is just the free dynamics of the bat, which of course you ignore. They claim that in this way, you can experimentally distinguish between standard quantum mechanics. So that's where you have a Hilbert space and you've got a self-adjoint operator as Hamiltonian, from what they call alternative quantum theories, or AQTs. They also conclude that Markovian models, so that includes the Gisant-Percival type of collapse models, Slava-Balabkin's theory of quantum filtering, and indeed the Hudson-Sarati class of models. These are not amenable to dynamical decoupling, effectively because they're stochastic. You've got some form of either Brownian motion or quantum Brownian motion involved. The dynamical decoupling never can happen fast enough to kill off the decoherence effect. So these are quantum field theory, alternative quantum theories. Now, this comes as something as a shock to anyone who's actually worked with quantum Markovian systems. Even if you're not a mathematical physicist, if you've been working in quantum optics for the last 30 or 40 years or so, more, you might have been using Gardner's approach to quantum noise, which uses quantum Markov processes as well, not in the Hudson-Sarati language, but to be told that you're not actually doing quantum mechanics and you're doing an alternative quantum field or quantum theory would certainly come as a bit of a surprise. The other knock-on of this, which was rather unpleasant, was people assumed that dynamical decoupling therefore doesn't work if you've got any sort of Markovian noise, so it's not actually a good technique to use in application. Again, that's quite wrong as well. So there's clearly something wrong here in this. As we observed in the prologue, the Hudson-Sarati theory is actually a Hamiltonian theory. The flaw in the argument is effectively the following. If you look at the Hamiltonian, so this is the Gregorati, von Waldenfels, Cherepanov Hamiltonian, it's a perturbation, all right, but it's not a regular perturbation, it's a singular perturbation. And this is crucial. When you look at the domain, as I said, comes with a boundary condition. This is effectively the input-output relations. And that's specific to the coupling operator L, which makes an appearance. So if you're going to conjugate before and after by one of these unitaries in the dynamical decoupling set, what you get is a different operator with a different boundary condition. And if you want the intersection of all these domains, it's going to be trivial. In fact, the only case where it's non-trivial is where your coupling operators, the L's, they were only looking at one. The coupling operator would have to commute with each and every element of the dynamical decoupling set. So with all of these unitaries. And in general, if that's the case, to be a dynamical decoupling set, the only way around this is for the coupling operator L to be a multiple of the identity, in which basically means your system and reservoir aren't actually coupled in the first place. So it's a sort of cautionary tale here that all this use of Chernov's theorem and one parameter semi-groups is very nice, as is mathematical rigor, but actually having a bit of insight into what's going on is pretty critical as well. So we did have a response to this with a colleague, Hendra Norden, in 2017. So the correction to this is the following. First of all, dynamical decoupling, as described in the paper by these four authors, at best it's only going to work for the regular perturbations. Genuine Markovian interactions correspond to singular perturbations, so the Chernoff term is not going to work. The quantum Markov models, rather than being alternative quantum theories that sort of lie outside the framework of quantum mechanics, this is not the case. They are quantum mechanical models, of course. We've been using them for decades now, exactly in that context. Sure, they can't be dynamically decoupled, but the standard quantum mechanics stuff. If you look in the physics literature, I have to say there's quite a lot of misunderstanding about what the concept of Markovianity is, and in particular, what the role of dilations of physical systems are as well. So I'll finish up with this as an epilogue. For a conference on one parameter semigroups, I would say in physics, there tends to be too much focus on the one parameter semigroup itself or its generator. For CP maps, you've got the Lindblad generator. And part of the reason is as follows. If I give you the semigroup, you're lulled into a false sense of security that you actually know everything there is to know about the dynamical evolution. And sort of this is, if you go from the Heisenberg picture to the Schrodinger picture, you can say, well, using the adjoint of the map here and knowing the initial state, then I can work out the reduced state of the system for each and every time. So if I know the state of the quantum mechanical system for each time, I know everything there is to need to know about the system. The problem is that that really tells you very, very little about the noise. I mean, if you go back and look at stochastic processes in general, the Kolmogorov reconstruction theory for stochastic process, or in the quantum context, it's the work of Luigi Accardi, Alberto Frigerio, and John Lewis. in order to reconstruct a stochastic model, it's not enough to know just the one-time averages of things. So these are just the one-time marginals. You need to know the correlations, the two-time correlations, the three times correlations. In other words, the finite dimensional distributions, okay? Otherwise, you don't know anything. You don't know whether the dynamics is Markov or whether it's actually coming from something trivial. You don't know the level of chaosity that's in the process at all. You really know nothing about the noise. So saying, well, sometimes we can dynamically decouple, sometimes we can't. Well, you really know nothing if all you know about is the one parameter semigroup giving you a limited amount of information here. So for things like quantum control, we have to have an accurate model of the noise. So when we're using dilations aren't interchangeable. The dilation has to capture enough of the correct physics in order for it to be useful. So I'll finish at that point. Thanks.
The question about term Markovian property, here it means existence of semigroup, as I understood.
No. This is probably one of the great difficulties. The term quantum Markov semigroup is used for just these type of families, but it doesn't necessarily imply Markovianity. For instance, for say a qubit which is being damped, you can come up with very simple models for this. You could say, well, the qubit is actually coupled to a single variable, okay, and it couples by the sigma z. However, this variable, random variable, you just take to have a Cauchy distribution. So when you look at the time development, you get this e to the minus absolute value of t, right? The characteristic for the Cauchy. So that looks like an exponential decay. But your environment here is just a random variable with a Cauchy distribution. It gives you exactly the same quantum dynamical semigroup as a full Markovian model where you have a Bose environment causing the dissipation on the qubit. This example actually goes back to Johan Lindblad, and I think it's mentioned in this famous paper of Riccardi, Frigerio, and Liu. Lewis, yeah. So
potential relations, yes.
Yeah. Why they use the term quantum Markov semigroup is because the family can also act as the set of transition kernels for quantum Markov process. But you don't know anything about the noise. You don't know if it is a Markov process. You don't know about the whole hierarchy to determine whether it's Markov.
So it means that the semigroup corresponds to a stochastic process, right? So you have a contraction semigroup and this corresponds to a stochastic process, or what do you have in mind?
No, the thing is you can have several different dilations of the same quantum dynamical semigroup. And sometimes these dilations may be trivial. They may not correspond to what's understood by a quantum Markov process, right? There may actually be no Markovianity in it, right? So Hudson Sarati gave a proper Markovian dilation so that when you start looking at not just the one-time behavior, because all the semigroup tells you is for a particular observable, what does it look like at time t? So you can say, well, for any state, you now know its distribution, but you can't say anything about the correlation of the observables, say, at two different times without further assumptions. Yeah, it's like effectively saying, look, I have a stochastic process. I know the distribution of the variable at each time, but I don't know how it's correlated at 2 times, 3 times, 4 times, etc. Yeah.
Okay. Thank you.
And it's astonishing, but physicists really think that, yeah, I have the quantum dynamical semigroup, therefore I have everything. You actually know nothing about the noise other than what it does to the one-time averages. You don't know what correlations are in the noise. Yeah.
May I ask a question?
Yes.
But physicists also have quantum regression theorem. How do you think
I mean, the quantum regression theorem, if you do assume some form of Markovianity, it's really just this result telling you how the higher order correlations can be broken down using the transition kernel. But the transition kernel is the 2-point. Yeah.
I mean, transition kernel plus quantum regression theorem, it is Markovianity or not?
Yes, but the physicists, at least the guys in these paper and many of the people who've picked it up, haven't got that far. They only think of doing classes of experiments where the experimenter is restricted to doing one measurement throughout the entire trial. The idea that an experimenter can do several measurements at different times in the same trial and look at the correlations, then there would, if you were picking up different correlations, you know, you'd have to have different dilations here. The dilation itself is extremely important and it has to capture the physics. And if you're talking about things like dynamical decoupling, memory and system, you really need to know more about the noise.
Okay, thank you.
Yeah.
Okay.